So here's our last problem. If we read over the problem, it should look extremely familiar to you. Sketch the shear and the bending moment. Diagrams for the beam, which is supported by the wall. So this is a cantilever beam. I said I do these from time to time. It's all based on what my mood is when I make up the exam. Use labeled lines below. So there were labeled lines for drawing this diagram. Label the sketches to show the point where the bending moment has a positive maximum and also determine the bending moment at this point. So they're all the same question. You'll get the same question. Just the question of what the beam is. That's what I change. All right. So for this one, we go after this in the usual way. We would go for the free body diagram. We take the wall away, and when we do that with a cantilever beam, we have a shear, so there's a force here, just like with a pin, and we draw the force in positive because that would be positive shear, but we must add the bending moment, okay? This is providing, the wall is providing a twist to keep this thing all up, all right? So we do that this way where it's pinching the top, but we'd expect the beam will be coming down this way. So this will wind up being negative bending moment, but then the signs work out for us. Okay. So here we have, go 15 meters. If we look at this problem, we had nothing for 10, a 10 meter distributed load right here. So 10 times 40, so there's 400 net. So you go 5 over, total 15, then your 400 newtons comes. Nothing for 5, nothing for another 4, so that'll be 9 meters to get to 100 coming up. Then 4 meters, and then we have this 600 Newton meter torque that's being applied that's pinching the top out here. All right, so here's our free body diagram. 15 meters to the effect of the distributed load, 9 meters to the point load of 100 newtons, which is going up, 4 meters to the final torque that's applied. All right, summing the moments at A. So the initial bending moment, then we have this going clockwise, minus 400 times 15. 100 is going counterclockwise, times 24. 600 is going clockwise, plus 600. If you solve this for MB, you'd come up with minus 3,000 Newton meters. 400 down, 100 up. That means V0 must be 300 up. So that's there. If we go look at the end, all right, we have a moment that's applied, but there's nothing applying a force. So there's nothing for this to oppose. Therefore, V28 is 0. This must oppose that. So this is pinching the top. It's counterclockwise. Therefore, this pinches the top and it is clockwise. So it's going to go as we drew it. So it must oppose this. So our bending moment at the end is plus 600 Newton meters. All right, so we're ready to start tackling the graph chart for this thing. And I've drawn a few construction lines in already. So let's move this up. Okay. So if we look at this thing here, if we walk the beam, well, first of all, we said the initial shear is 300. You can barely see that in the video. We'll just drop that down. The initial bending moment is minus 3,000. So we'll go down to here, put that in. The final bending moment is 600. That's right here. And the final shear is 0. So I've taken that step. So we've done the endpoints. Now we're going to go through and walk the beam. So if we look from a force point of view, bring this into view. I've started here. I have 10 meters of nothing. So we're at 300. And there we go. So we have the 300 in. Then we hit our distributed load, and we're going to drop 400 over 10 meters. So 300 minus 400 to take us to minus 100. And there that is. All right. Then we have 4 meters of nothing, and then up 100. $28 meters there. Okay. So there this is. We need a little more data here. We need to figure out where this crossing point is. We're going to need this area A1. We'll need this area A2 right here. Okay, so let's figure these things out. We're at 300. The slope down is 40, the distributed load rate. So we will come in here and we have this line is 300 minus 40, starts at 10, so x minus 10. We'll set that equal to 0. And you can use a calculator and check it out, but it works out to 17.5. All right, and we'll just follow this point down. Okay. Triangle A1 is 300 high, 10 to 17.5, that's 7.5, divide by 2, and that works out to 1125. And A2, this one in here, is goes down 100. That's 2.5 across. Divide by 2 is 125. So we have the key information that we need. And obviously this is 20 to here, so we've got minus 400 in there. So we're ready to walk the beam again and take care of all the moments. So first section, as we go, before we went across with force, now we go across to integrate shear. 3,000 for 10 meters. So 3,000 times 10 is 300 times 10 is 3,000. So we start at minus 3,000, we add 3,000. Boom. All done with that. Okay. This is going to be where our peak is. Okay. And we're going to add on 1,125 in here. This area here is 1125. So that seems like that's a good spot for it. So I'll put that right in there. So now I need to draw this in. So I match the slope. And there that is. All right. So this is at 1125 Newton meters. Now I got to lose 125, so that'll take me to 1,000. Put that right in here. Okay, now I'm going to lose 400 more, so here I am at 1,000. So that'd take me to 600. Well, that's going to work kind of nice, actually. And a little off there, but there we are. And so I'm matching the slope here, so that's good. Now nothing happens, so I go over, and bam, I hit my 600. And here's our plots. So the last thing we have to do is, it says, tell us all about the maximum bending moment. So max bending moment equals 1125 Newton meters. Get our units in there at x equals, that was at 17.5 meters. All done. And that completes the work for the second midterm. I'll comment on the midterm shortly.